Very good morning, good afternoon, and a good evening to everyone watching us from different time zones all across the world. On behalf of my team, I would like to welcome all the viewers to our class, which says Design Optimization of Aircraft Landing Gear using Generative Design. My name is Harsh, and I am an aerospace engineering student at the Dayananda Sagar University, Bengaluru. And my co-speakers for today's presentation are Abhishek and Kushal. Abhishek is a mechanical engineering student at the AISSMS College of Engineering, Pune, whereas Kushal is a mechanical engineering student at the National Institute of Engineering, Mysore. And in nutshell, this is our first time presenting at AU, so we hope viewers will like our concept and the presentation. One of the biggest factors in terms of design that every designer would like to do, it is to optimize his design. And we all know about topology optimization. And those who don't know about it, it is a mathematical model that optimizes the layout of the material when certain conditions like loads, constraints are defined. Here is a simple example of topology optimization that you're seeing here. And yes, in topology optimization, we do work on a design, but the maximum amount of information that we give to the machine, but in response, the maximum amount of output that we'll get is just one. Now, I would like to take a moment to sum up the topology optimization so that we can compare it to generative design. The topology optimization is used by many CAD tools available in the market. But like I said before, the maximum amount of information that we give to the machine for topology optimization, but in response, the maximum amount of output that we'll get is just one. But whereas when we compare topology optimization to generative design, in generative design, we will be challenging the machine by providing certain conditions to the computer, and the computer uses machine learning algorithm to give us back many variations of the design. Now, it's highly designer's choice to choose which is the best design rather than spending more time in terms of thinking about the design that actually saves time. Now, let us look how we are trying to apply this new technology to select a case study for our team. Here's the first one. Many of us already know about the retractable type of landing gears, but those who don't know about it, these are the type of landing gears which retracts back inside the aircraft to its resting position, and they can be found in various large commercial aircrafts and private jets. This type of landing gear has got some mechanisms and connections which helps to retract it back, and it is being used in many aircrafts which you will see today, including the Airbus A321, which is depicted here in the picture, and also the Airbus A320 and more. Another example of a landing gear is a high nose wheel type retractable landing gear, but this is again on a similar site, and this type of landing gear is mostly used in the fighter jets and the supersonic aircraft. We didn't consider retractable ones because they are so big in size and they kind of entirely rely on connections which and the mechanisms which helps to retract it back. So we didn't consider them as for now. Then of course we tried looking at some more landing gear type and we came across the rigid ones. Or in better words, I should say, the other two landing gear types, which is visible from the picture, are the type of landing gears which doesn't retract back and stays in their position as it is. Then of the all four, the best applicable landing gear design for a case study would be on a fixed type of landing gear, which is the third one. We decided to go on and try the experiment further on a fixed nose wheel type landing gear to get a case study out. Then we'll start thinking more about going back to retractable type nose wheel types. And I'm pretty much sure the experience which our team has got on applying this generative design technology will help us in applying this knowledge in future to different type of advanced commercial aircrafts and defense aircrafts in future. Now, to sum this slide up, we decided to go with the fixed type of nose landing gear to continue our study. Now, among the fixed type of landing gears, we know that Cessna is a very well-known company which has around 95 years of experience in making short-haul commuter aircrafts, and they still are using non-retractable type of landing gears in some of their aircrafts, maybe due to a variety of reasons. Further, we choose a component on this Cessna Grand Caravan aircraft that you're seeing here. Cessna has many aircraft in the market, and if we are able to solve out some of the issues related to drag reduction using generative design, then it will be a good case study, and we may go back to Cessna to show them the results. Now, my co-speaker Abhishek will tell us more in brief about how we are applying generative design to a case study.
Thanks, Serge. The way everyday items from chairs to cars to powerful tools are made is being reimagined through a new process called generative design. Using artificial intelligence software and the compute power of the cloud, generative design enables engineers to create thousands of design options by simply defining that design problem, inputting basic parameters such as height, weight it must support, strength, and material options. And by applying all this, we are looking for a few objectives here in our project. We are aiming for reduced weight, improved efficiency, and customized product development. Imagine if instead of starting a drawing or CAD design based on what you already know or ideas that are in your head, you could tell a computer what you want to accomplish or what problem you're trying to solve. So before going to the generative design approach, let us have a look at the overview of the generic design. We studied this wheel holder bracket of the Cessna aircraft and redesigned it. From the design, we observed that the weight of our part was 963.27 grams. And with the choice of material being aluminum 6061 and die casting being the manufacturing method. Considering the latest manufacturing methods like additive manufacturing, we decided to apply generative design to the study and how the design varies from the additive manufacturing method. Now that we have an idea for our standard engineering approach, let us move on to see how the generative design study has been set up for our case study. The preserved geometry, as we know, is used to represent regions that will be retained in the final design. In our case, the preserved geometry feature is used for defining certain holes or empty places where the axles, shafts will pass through. In the obstacle geometry, representing the areas to be avoided by the generative design process, it is used for regions where the other parts are getting assembled, like connecting rods, damper parts, and so on. Before talking about the initial shape, I will take 2 minutes to talk about the generative design. We describe generative design in a way as a design exploration process. That is wherein the algorithm comes up with various forms of the same design, which we would not have considered or be able to achieve. Also, recalling the objective of a case study, it was to optimize the landing. Stressing on the word optimize, it means that we are looking for improvement in the existing design. And coming back to the generative design discussion, we define our initial shape, as you can see over here in the yellow color, and we would give this already existing part so that the machine has a starting point already from where it can take on for enhancing the same. We then apply certain loads and structural constraints on our part. Along with this, we also provide few other inputs to the software, such as the design objective being to minimize the mass with a minimum FOS of 2 and providing manufacturing method and materials. Since we are just optimizing the design, we went ahead with aluminum 6061 itself as the choice of material and additive manufacturing as the methods for manufacturing. This saves us a lot of time. Once the generative design process gets completed, we get multiple design outcomes from which we are free to choose. The picture in the slide shows that 4 such outcomes for aluminum 6061 material. From here, we have multiple ways of selecting that one design outcome which suits our requirements. We can choose our outcome based on factors such as minimum FOS achieved, minimum displacement the part undergoes, and so on. Here is a small clipping which demonstrates the various parameters and how we made our selection from the outcomes. Before playing the video, I would like to take a moment to list down the parameters what we are going to focus on. Thus, minimum FOS as per our case study, then maximum was 1 miss stress, and maximum displacement global. Here in the scatter plot view, we can see that 4 outcomes for aluminum 6061 material. To see the best one, we keep one outcome as our reference and compare it with others to finally choose the best one from various parameters. We want the one with the highest FOS, least one misses stress, and least maximum displacement. We choose this outcome and decide to go ahead with this. Now, my co-speaker Kushal will tell us more brief about the post-processing and simulation for the generative design process.
So once we choose our outcome and generate the output, it so happens that sometimes we need to relook at the design for some areas which might require some rework. But it is not that every outcome will have changes to be made. Sometimes we will get an outcome so good that we can continue with the further processes. During this rework, however, we do not spend a lot of time since it involves only some cleaning up in very minimal areas and not the entire redesigning. The areas where the post processing has been done are highlighted in the picture, as you can see. Due to some unnecessary material available, the results get affected majorly during the analysis of the part. To avoid this major error, we decided to do the cleanup, or what you can call it as rework in some places, by removing these unnecessary materials. One extra thing that must be noted here is that this unnecessary material can cost a lot during the manufacturing as well. As I said a while ago, the unnecessary material affects the analysis results. To know more about the differences in the results, please refer to our handout. After the post-processing was completed, we went on to perform the analysis on the designs, both our original design and the design process through generative design. First, let us have a look at the simulation study performed on the design using standard engineering approach. To the design, we applied certain loads and constraints, which being the same as that we applied during the generative design study setup. From the results, we now look at two major factors, the stress distribution and the displacement plot. First, looking at the stress distribution, we see that the maximum von Mises stress generated in the part was 103.5 megapascal. Next, looking at the displacement measure, we can observe that the part undergoes a maximum global displacement of 1.805 millimeters when subjected to the loads and constraints. In a similar way, we performed the analysis for the processed outcome from the generative design. Here also, we will be having the results for the same two factors, the stress distribution and the displacement plot. In the stress distribution, we see that the maximum von Mises stress generated is 90.5 megapascals, and in the displacement measure, our part undergoes a maximum displacement of 0.7894 millimeters. Just like how we had a review of our standard generic design earlier, let us now have a quick overview of our design from the generative design process. As said earlier by my co-speaker Abhishek, our case study involves the study comparison using the same material. Hence, the material remains the same. That is, it is aluminum 6061. From the properties of the design, we found the weight of the new design to be 741.45 grams. From the previous analysis results, as we have seen, the stress generated is 90.5 megapascals and the part undergoes a maximum displacement of 0.7894 millimeters. Next, let us have a quick comparison of our initial design with the new one. The first and the major difference is in the geometry of the two designs, which is so clear from the two pictures here. This allows us to go for different manufacturing methods like additive manufacturing. Talking from the perspective of the weight, the initial design weighed 963.27 grams, while our new design is 23% lighter. That is, it weighs 741.45 grams. Next is the displacement perspective. There was a 56% reduction in the displacement of the two parts. Our original part underwent a 1.805 millimeter displacement, while the new design underwent a displacement of just 0.7894 millimeter. Here is a small video on how the model evolution takes place during the generative design process. This is a picture of the full assembly of the nose landing gear, where the initial wheel holder is replaced by the one redesigned using generative design. Once our design was completed, we further went on to get a prototype of a design 3D printed. The picture on the extreme left is a snapshot from the Slicer software, which we used just before 3D printing. And the other two pictures, what you see, are the pictures of the final 3D printed part. This being a prototype, and since we are students, we used PLA for printing. After the 3D printing, we did some minor working on the part, like giving it a surface finish using sandpaper. These are the few references which we refer to during the entire phase.
Very thank you everyone for patiently listening to our presentation. And we would also like to thank all our mentors for helping us throughout the case study. And as we had limited time for this presentation, so we couldn't include everything, we couldn't tell everything in detail. So if you want such more details, like what calculations we have done, what loading conditions we have given, and more, so you can refer to our handout. And thank you everyone for listening to us.